தகப்பங்கிட்ட பேசாம
Yes, sir.
Okay. Good evening, all of you. It is audible.
Yes, sir.
Yes, sir.
Okay. Today we discuss the torque in three-phase induction motor. Torque produced by three-phase induction motor. Okay. Three-phase induction motor. Okay, dear. As we know, in DC motor, in DC motor, torque is, armature torque. Armature torque produced in motor, it is directly proportional to the armature current and flux. Okay, phi Ia, correct? Similar to here, this torque produced by three-phase induction motor depends on following factors. Following factors means first is it is the magnitude of resultant magnetic field in air gap. Magnetic field, flux, okay, or flux in air gap. That is, phi r. Okay. Second, rotor current. Like here, armature, this is a rotor. This is rotor current, means I2. And here, because it is AC, so here it depends on also power factor. It is rotor circuit power factor, means rotor power factor, cos phi 2 also. I1 is the overall power factor, means stator power factor. Okay, so like one by one. If we write the mathematically, we can write now. Hello, this torque, or it is a electromagnetic torque. That it is called electromagnetic torque. It is proportional to this magnetic flux in air gap resultant I2 and cos phi 2. Okay, dear. This is one. Now as we yesterday draw the equivalent circuit. Okay, means your stator resistance, then leakage reactance, then this is your magnetizing branch. Okay, here. And this may be your rotor. This is stator. Then rotor circuit also. So this is your stator. Okay. Then rotor is, or separately we draw the rotor circuit. Okay. Here, we apply the V1. Now here R1, X1, this is your magnetizing branch, R0, X0. So when we take a current I1, okay, my dear, actually, voltage across this is E1, induced voltage. Okay. You know, when we apply the voltage, this, if we neglect this drop here, here, this drop, if we neglect the drop in stator impedance, this two voltage are very close, means equal. Okay. V1 equals to E1. And as I told now, here, this current is flowing here, I mu. Okay. So voltage across each branch is like E1 or V1. Huh? Correct, no? So actually, you know, this flux, when at no load, when your motor is at no load, generally it take a magnetizing current. Okay. Correct, no? This is your rotor circuit. Separately, we will draw, like we are drawing. Your rotor circuit we show here. This is your induced voltage in rotor, then resistance. This is reactance of rotor. This is your rotor circuit. Okay. So here, this is your voltage across induced voltage. Then this is your I2, R2, XX2. Okay. R2, XX2. So actually, this resultant flux is directly proportional to this current. This when it take a magnetizing current, or it is proportional to your V1 applied voltage. And you know, V1 equals to E1 means we can replace this E1. Means this phi R is proportional to E1. Okay. Now you know this this E2 and E1, the induced voltage in primary and secondary. Okay. So this E2 by E1 equals to K. Then E2 equals to K time of E2. Or we can, sorry, K1. It means E2 is proportional to E1. Correct? By turn. So we replace this phi R equals to this E2. Or some constant we take. Okay. So now, if we remove this, there may be a K. Okay. Like this. For E2, we can replace with E2. Okay. It is proportional to E2. Okay. Now, please, you refer this this R2 circuit. Here, if we calculate what is the impedance, this rotor impedance, you know, it is a series reactance circuit. So here it is R2 square plus XX2 whole square. You know, no? Hello? You know, this is your resistance of rotor. This is your reactance of rotor. Reactance. This will be your impedance. Correct, no? This is Z2. This is R2. This is XX2. Correct, no? This is phi. Then power factor, rotor circuit power factor will be your R2 by Z2. Correct, no? And the rotor current here. E, if we write here, we replace this resultant flux with the E2 and I2 rotor current we can write. That is impedance, your total voltage, applied voltage divided by impedance. Correct, no? Your impedance is R2 square plus XX2 whole square. Hello? Yeah. Hello. So this is, or we can say, now power factor is, it is also your R2 by Z2. Z2 means again this, R2 square plus XX2 whole square. Okay. Now when we replace these values here in this torque equation, okay, by substitute this all values by the values of phi r, I2 and cos phi 2 in equation 1. Then we get a T is proportional to, you know, for this we can write na KE2, okay, plus into R, current is slip times of E2 by this impedance, R2 square plus XX2 whole square into R2 by this power factor is again this also, R2 plus XX2 whole square. Please mute yourself. Okay. So now see, when we multiply this, it become a, or we set equals to, then overall coefficient, proportionality coefficient will come K1, slip times, then E2 square, R2, this is numerator, and in denominator, it is R2 square plus XX2 whole square. So my dear, this is the torque equation of your three-phase induction motor, the torque developing. So as I told now, this torque is directly proportional of the rotor resistance, also your slip. Now, suppose 8 is starting. 8 is starting. Okay. 8 is starting. When speed means motor is just we switch on, so at speed is 0, then slip is 1. Therefore, the torque developed at starting, it is called starting torque, equals to K1, slip is 1, then E2 square R2 by R2 square plus XX2 whole square. Okay, so this is your starting torque. Okay, dear. Now this is asked one question. Starting torque depends on what? So it is your actually the torque is depends on your see, flux means your supply voltage, current, and power factor. The torque is depends on. Correct? Okay. And this is your E2 square. This is square, okay? E2 square. Now,
sir, can you show the triangle part? Triangle part.
Okay.
Okay, sir.
Now, under running condition, when motor running with slip S, or maybe it is at full load. So there is a full load slip, we can write FL. So there will be a full load torque. Okay, that is again here K1. Here we write the full load slip. Okay, into E2 square R2 by R2 square plus, here you write full load slip, then x2 is whole square of this. Okay, so this is your full load torque, my dear. Correct? You have full load torque. Now, in actually question, there was one question in your exam. This starting torque depends on what parameter and how it is related to your full load torque. Correct, no? Hello?
Yes, sir.
What is the question? It is in which paper actually? No? I think here in October.
Yes, sir, in October.
Yeah. Yes, in October. Yeah. List the factor determine the starting torque of three-phase induction motor. Then how does it torque generally compare with the value of rated torque? So actually starting torque is higher than the full load torque. It is like 150% or maybe sometime it is 200%, double. Okay, correct. Please keep mute yourself. Now, see again, as you know, we can calculate this torque also from your rotor input or gross mechanical power. Okay, see rotor input or air gap power. This power input to rotor. Power input to rotor. Hello, what is the rotor input? P2 equals to Tg, gross torque into omega S. Correct, no? Okay, dear. Or it is also, we can write the slip times of rotor copper loss. Correct? Then we can calculate, therefore this gross torque, Tg, this gross torque, we can write slip times of this PCR means rotor copper loss. So what is the PCR? Hello? PCR equals to 3 times of rotor.
3 square R2.
Yeah. So if we put here 3 times of I2 square R2 divided by omega S. Okay. So generally synchronous speed is constant. Correct, na? Rotor resistance is also constant if we not change like in a squirrel cage type motor. So it means your this torque or gross torque, it is only proportional to slip and I2. Correct, I2 square. Okay, dear. Generally this two parameter, slip and I2. Now 8 is starting. Therefore, starting torque in terms if we calculate starting torque TST, the slip is in TST, slip is 1. It means this is a rotor current at starting whole square. Correct, no? At starting current. So this is 1. And 8 under running condition. 8 full load under running condition. Okay. So this is T at full load, TFL. It is proportional to your full load slip we take here. And what is the rotor current at full load?
सर पीसीआर इक्वल टू SP2 होता है ना?
PCR equals to no
PCR divided by slip है ना?
sorry slip times yes, it is divided by slip. Okay, sorry. Okay, actually this is PCR by slip. Okay, then it means it is multiple by slip. Okay, then we can torque by this by slip. Okay, this is the equation. Please correct it. Sorry. I2 square by slip. Okay, this torque is directly proportional to I2 square by slip. At starting, the slip is 0. It means it is only this. But at full load condition, we take here at full load, what is the rotor current divided by full load slip. Okay. Now if we divide this TST by TFL, okay, then you know what it comes. I2ST square by I2 full load, correct? And is into full load slip. So it is slip times of this is sorry, whole square. No? It is a whole. Both are square. No? That's full load slip. Here it comes square time of this. Okay, whole square into full load slip. So you know, my dear, this because full load divided by slip, it is come up. Now you know it depends on your what is the starter you use. It is star delta or it is a direct online starter. Your TST starting current, okay, is greater than, or it is 6 times maybe, or it is √3 times in star delta, or in, it depends what is the method of starting. Generally it is greater than the full load current, correct na? Hello, starting current is higher than the full load current. That's why your full load, see, starting torque is higher than the full load torque. Okay. So we can show with this okay relation. Now come to the condition for maximum torque. This also asks, no, what is the condition will be fulfilled for maximum torque. Now we discuss the conditions for maximum torque. So actually your torque is, general torque equation is K1. Now here I write this K1 is a proportionality constant. Here this K is proportionality constant. It is its value is 3 by omega s. Okay, or it is 3 by 2 pi ns, because synchronous speed is also constant. Now this general torque equation is K1 slip E2 square R2 by R2 square plus slip times of XX2 whole square. Okay. So now for maximum torque, if we differentiate for maximum torque. If we differentiate this with the slip, okay, actually this torque is vary with respect to slip. Correct, na? So if we differentiate this torque with respect to slip and set equals to 0, okay. So if we do not like the means d by ds with respect to slip, to we have differentiated this. Sorry, no, here this r is not a square, okay. R2 by R2 square plus slip times of x2 square. If we differentiate and set equals to 0, so we actually there is a the derivative method of numerator and denominator. Okay. Okay, no derivation is asked. They just ask the condition only. Okay. Yeah, or we can easily differentiate it with respect to slip by UV by V method. If you have a good in mathematics, you can differentiate it. Then the final condition we get your rotor resistance equals to slip times of rotor reactance. Okay. So this is the condition for maximum torque. When your rotor resistance become equals to slip times of rotor input. It means from here, then this is the slip we write as a SM because it is not a maximum slip. It is the slip corresponding to maximum torque, that is R2 by X2. So this is the slip corresponding to T maximum torque. Okay. Now this is the condition. Okay. But what is the magnitude of maximum torque? Then if we put here values, okay, in this equation. Hello. If we put this condition here, if we apply this condition in this equation, so here we get a. So you can easily we can apply this condition. Hello. See how? If there is a K, it becomes slip times of E2 square R2. See what you do na, in denominator you take a X2 as a common, X2. Okay. Correct. Or X2 square. Okay. Then it is come R2 square by X2 square plus here only slip square will come. Okay, dear. Or now we can write K1 slip E2 square. Now this R2 we can write as a X2 also. Divide by X. Now one this one is apply here. This then this is a slip also, na? Slip square plus slip square. Okay. And this is also slip. So my dear, we can write na K1. Now this slip and this is also slip. Okay. So it becomes S square E2 square divide by, now this becomes twice X2 S square. This slip square is cancelled. What is the magnitude of this maximum torque will come? Finally, this T maximum will come K1, no slip is now, E2 square by 2x2. So this is the equation for magnitude of maximum torque. Okay, dear. This is the 5. So there is a starting torque, there is a full load torque, there is a maximum torque. Okay, dear. So means your maximum torque is not depends on slip. Okay, here this slip is not there in it. Now, if we draw torque now torque versus speed. Speed, or sometimes it is called we can draw with slip also. The torque versus speed or torque versus slip characteristics of three-phase induction motor. It is a very easy. Okay, dear. This is zero line. Here, here means here speed is 0. It means slip is 1 maximum. Maximum slip is 1. Okay. Here speed is 0 and slip is 1. Okay. Speed is 0. But here when your speed become close to synchronous speed, then slip is 0. So actually your speed is increasing in this direction. Here is speed from 0 to synchronous. But your slip is in this direction. Slip. It is minimum 0 to here 1. Okay. And here we take torque. My dear, at starting when speed is 0, in torque equation. Okay. In generally your torque is actually in starting your torque is inversely proportional to slip. Okay. And under running condition, okay, running torque. This is starting. Under running condition, this torque is directly proportional to slip. Okay. Why? From this, actually, when we apply starting condition. Okay. So this is this like here from this equation also. See, like your starting torque. It is starting, it is inversely proportional. Okay. That's why from this we can calculate. Like this is your general equation, no? Torque equation. Here, see. Here, if you in this equation, see actually at starting, at starting your this is the maximum slip. It means generally your this rotor resistance is suppose it is 1 ohm and reactance is 10 ohm. Okay, like this. My dear, at starting your this slip times of x2 square is greater than 1. Sorry, R2. We neglect R2 square. We neglect the R2 square at X starting. Then see, this will remove. It means it is directly proportional. Then we remove this from this. So your this torque equation is directly proportional to slip is cancelled by E square 1. So it is inversely proportional at starting. Under running condition, when your slip is 4%, full load slip, okay? Then when we multiple this slip times now then this xx2 square is become less than R2 square. Okay, so this will be neglect. When this neglect, this torque is directly proportional to slip. Just you remember these two things actually. So it is at starting the torque is inversely proportional to slip at starting. Under running condition is this. When motor is running with full load or with slip S. So this is the running condition here. It means here it is directly proportional. Means your slip is increasing this side. It means when slip is increased, torque is increased like this. And it reach at maximum, then it start to reduce because it is now inversely proportional. So this curve is like it is a rectangular hyperbola. Okay, correct. So means this is your starting torque. Suppose so it is start from here. Then there is a dip one. Then it is increased, and it reached as maximum. Then it is reduced. Like this, okay? So this is the torque versus speed characteristics. Now this is the maximum torque here. T maximum. This maximum torque is also called as a breakdown torque. Breakdown or locked rotor. Okay, torque. T maximum. This is your T starting here at speed 0. This is starting torque. This is the pull up torque. Pull up torque. Now your full load torque, you see, motor is running like here. So see, this is your operating here. Motor is operating here. Then this is your full load torque. TFL. This is your full load torque. Okay, this value is cut here. Okay. Because see here about from here this part region. Okay, from suppose it is A to B. And then B to C. So this region A to B is unstable. Here is operation is unstable. Unstable. This is stable region. So actually motor is operate in running condition where from between to B to C, either here, here or here. Okay, like when we increase the load on the motor, suppose we increase the load, then this curve is shift to here like this. Okay, so see earlier suppose motor is operating here, then speed is this. This is your actual, this is synchronous speed or no load. Here this is your actual speed. When we increase the load, see speed is decreased or slip is increased. So as we increase the load, your speed is decreased. That's why. But here it is just reverse. That's why here is unstable. Okay. Method of speed control. Sometimes they can ask, no? So my dear, first is like stator voltage or terminal voltage control. Stator voltage control method. Here now we vary the V. It is variable. F is we kept constant, fixed, not vary the. Only we vary the frequency, voltage. And see, vary means not we increase from rated. We can apply the reduced voltage. Okay. Over voltage and over frequency never we apply. Okay. Suppose this how we reduce the voltage to motor. So this is your 3-phase induction motor. This is coupled with load. So now either you have a primary resistance here in series with the stator, okay, or auto transformer, or either you have a primary resistance. See here. Then we apply this voltage, reduce voltage. Okay, dear. Here you apply RYB. So this is the here we add the resistance, then we can vary the voltage or by auto transformer. Okay. And my dear, again one method also I tell you. At no load, by voltage control, we cannot able to control the voltage. Speed. Hello. If suppose you want, see only on load condition, the speed is controlled, reduced by voltage control. See if there is no load on motor, then it is at reduce voltage, it is rotate with the same speed. If you apply the reduced voltage, then also it no change here. Only when load is there, then only we can. This is the another disadvantage of voltage control. Okay, dear, understand? At no load condition, you cannot able to control the speed by voltage reduction. See, we can explain how the speed is controlled by voltage by voltage control with the help of torque versus speed. See, here n is 0, slip is 1. Suppose this is your general torque versus speed characteristics. This. Okay. Now, actually, this characteristics with rated voltage. If you reduce the voltage, this curve is shift like this. But here it is at common point. Here it is maybe suppose 75% voltage you apply. If you further reduce the voltage, this curve is shift like this here. So it is at suppose 50% voltage. Now suppose your motor have a load. This is your load torque. Hello. So see how the speed is controlled. See, initially when we give the rated voltage, motor operate at here for same load, full load. Then here, then it is shift here. So see, this is the your speed is reduced. It means here, okay. But here is a narrow. This is the range of speed control only. Range of small range, not a wide range of speed control. This is another disadvantage of voltage control. And see, to deliver the load, motor draw the more current when you reduce the voltage. It is like under voltage condition, correct? So here current, input current, stator current is also increased. Okay. Now if we discuss second part, that is frequency control. stator frequency control. Here only we vary the way f is variable and we take a constant. Only frequency we vary. Okay, dear. So in this condition, actually, suppose this is your, this we also explain with the torque versus speed. My dear, this is supposed with the rated voltage and rated frequency. This is the curve. Okay, your speed torque characteristics curve. Okay. Now, this is with rated voltage, rated frequency. But when this is the speed. Now, when we see, we reduce the frequency. Like here, we reduce the voltage. Here, we reduce the frequency, applied frequency by frequency, cycloconverter or whatever it is. Then what happen? Actually, it is not a product. This is with rated. Like this. Now, what happened now? If we vary the frequency, then synchronous speed is 120 f by p. P is fixed. You reduce the frequency, then synchronous speed is changed here. Here n equals to ns. So when we reduce the frequency, means your synchronous speed is reduced. So this curve is shift to, okay, like this. Further reduce, then it is shift like here. Further reduce, it is shift like this here. Okay, dear. So means we get a high starting torque by this frequency control. TST is increased, and this maximum torque also increase for this. And we get this is your supposed load. This is your full load. This is your full load on motor. Okay. TFL. Then see, if we reduce the frequency, see, initially your motor is running at here. This is speed, then it will change here. Then it is shift here, then it is shift here. Okay. So this is your speed, okay, at different frequency. Okay. So again, the region is, okay, we can control the speed. But here, as I told, the flux density in motor, ear gap or core, it is, please remember, it is depends on V by F. Okay, please remember this. Before the invention of BFD, this was a lake. Means we only vary the voltage or either we vary the frequency. But it was, there is a adverse effect on your motor. See, actually it is, we can vary. This we maintain because when we design the motor, we select the flux density. Okay, like it is 1.1 Weber per meter square. Accordingly, we have to the size of motor is decide. Means dimension like core dimension and yoke dimension, like this length of and diameter of your motor yoke. D diameter. These are the two parameters. Okay. So it design the iron part also. How much iron core, iron part will be there, volume of iron. Because for a flux density, your main dimension is changed. When we decide the flux density for a, like suppose you design a 10 kilowatt motor, then we select the flux density. Okay. But when we vary this, suppose we reduce the flux, we reduce the flux, it means there is a, we reduce the frequency, then there is a overfluxing, means flux density is increase in the ear gap or in core. Then if it is known as a overfluxing. Then due to overfluxing, hysteresis and eddy current loss, they are depends on flux density. Like eddy current loss, it is K, your eddy current constant, hysteresis constant, plus B maximum raised to power 1.6 F frequency into volume of iron. Here it is eddy current constant into B flux square F square T is the thickness of lamination here. So actually that depends on the flux density. It means this core loss means overfluxing mein this core losses are increased. The motor get heated also. Okay, that's why we vary both in same proportionality. That is called as a third part, VYF control, or it is called VFD, variable frequency variable voltage drive. Okay, so here we vary both. Then suppose VFD's question come, this you have to explain. Now we vary both. How we vary? Suppose this is your supply. I will explain with single line diagram. This is a three-phase AC. This is three-phase AC. Then we put a converter. Converter means that is SC thyristor or SCR we use. Gate terminal like controlled rectifier. Three-phase controlled rectifier converter. Okay. Then we get a DC bus, DC voltage here, DC. Okay. Then again we have an inverter. We have an inverter. It is a three-phase inverter with IGBT based with pulse width modulation to get a sinusoidal three-phase. So this vary, the converter is vary the voltage here. It may be here 600 to 800 voltage we get DC. Then it go to inverter. Then we again get a three-phase AC. And this is your motor. Okay. So here we get a both variable voltage and frequency variable both. Okay. In this case, both this is your actual speed torque characteristics, and this is your this is your maximum torque. Okay, T max. So it is here when we reduce, like we have a 400 volt 50 hertz for simple. So if 400 by 50, it means it comes 8. Then if we reduce the voltage half, then we half the frequency. Then again we get 8. Then if we 1/4 the voltage, then 1/4 the frequency, again you get 8. Sorry. 200, then it is 225 and 12.5. No? Then you again get 8. Okay? Like this. So we maintain this ratio is constant. Then in this case, this curve is shifted. Okay, like this. With different frequency like this. Okay. And we get a wide range. We can run the motor at 20, 50 RPM also. Here is speed is 0. Here N is equals to N. So see, we use on same load. This is your suppose load. Then see, this is the speed. So there is a wide range of speed control also. Actually, VFD is recommended for variable load. Variable load means, suppose you operate the from this motor some pump or blower, fan, okay, like a pump or fan, okay. When the load on this, it is flow rate, Q, flow. You want to control the flow. So earlier we use a wall or damper here, okay. Then we add the resistance. Your motor take a same power from supply. But when we use a drive here, VFD, then we can control the speed. So your flow, this flow, okay, Q is the flow rate here. It is directly proportional to speed. And your pressure develop here in this. It is pressure is proportional to N square. And power, this is pressure means pressure head, H you write, and power drawn by the motor. It is it is directly proportional to cube time of speed. It means if there is a 10% reduction in speed, 10% reduction in speed by BFD, then your power reduced by, this power is reduced by 27% square time. It is a calculation. When we calculate, your power is reduced by 27%. So that's why BFD is known as a energy conservation or energy saving. But condition is variable load. अगर आप इसको full load पे always we operate at, here is a constant load, constant flow. If you connect the motor with a such load, it is a fixed constant load, same kilowatt. Then motor always run at full load, full speed. Okay, then no saving. That's why VFD is not recommended, because it is continuous in line. There is a power loss also in VFD. And other disadvantage, it introduced the harmonics. It produced the harmonics. That again, harmonics are high frequency components. They enter the motor, again they increase the core losses, hysteresis and eddy current loss. Then your motor get heated. That's why we required an active filter along with VFD. Filter circuits. Okay. They are costly. Okay, so this is the advantage and disadvantage of VFD drive. Sometimes they ask you, okay. So now you understand this in three things. Now there is a speed control also by rotor resistance, fourth one, rotor resistance, but it is applicable to rotor resistance. It is applicable to only slip ring induction mode, wound rotor, where we can add the resistance in rotor circuit. This is the torque. Here it is a speed. So with the rated voltage and rated rotor resistance, fixed value of rotor. This curve is like this. Okay. My dear, when we vary the resistance, this curve is shifted like this way. Okay, so we can get at starting, we get a maximum torque. Okay, T maximum also at starting. But why? If we increase the rotor resistance. Okay, so see here your R2 is increases. Like this is R2, this is R2 days, R2 days, this is R2 double days, this is R2 triple days, this is R2 four time days. So means R2 is less than R2 days, then it is less than R2 days, and it is R2 double days, R2 triple days, or it is R2 four days, like this. Okay, so if we increase the rotor resistance, this curve is shift like this. It means if suppose this is your load again, so your DC speed are reduced here. Correct, na? This your operating point is shift, na? With take a new curve. Then see, this is your speed. Okay. Here is speed control by voltage control, frequency control, resistance control, or V by F control. Na? Okay, dear. Okay, dear. Hello, any numerical question you want to discuss? Yes, please.
Sir, ETO MET1 6B question.
Okay. EMT 6, this one. No, it is 3-phase induction motor. Yeah. 6-1 is correct. Nice question. See, what are the factors determine the synchronous speed of motor? It is very easy. Now this part B. Excellent. Please. Suppose this kind of question asked. He said that star connected rotor means he is talking about your rotor is a star connected means it is a wound rotor, my dear. Okay, and wound rotor is always connected in star. So let us we draw. This is your this is rotor side. Okay. Generally, stator has a winding. Okay, in squirrel cage motor, but in wound rotor, rotor also has a three-phase winding. This is your shaft. Okay, on this shaft there is a slip rings are mounted. Correct, my dear? And this winding is connected to the rotor resistance starter or external resistance. Correct, my dear? Like this. Okay. This is the, under running condition, we short this. In starting, we add this resistance. So per phase, this resistance supposed to R2. Okay. Now we say that if we measure the potential between these two slip rings here, suppose this external resistance is, we have to remove the, now see, if we measure the voltage here and here in this 2 points between two slip rings, what it gives? So actually E is given 50 volts. It is a line voltage, my dear. Okay. So if we do now, then therefore E2, this E2 equals to 50 divided by root 3. Okay. What we write here? What is it is given? The motor has a induced EMF if you want between the whose limit is start stand condition. So actually now there is a R2 is a rotor resistance. Okay, my dear, resistance. Yeah, always it is per phase. Okay, and it is in ohm. Same like here, if we write na XX2, it is rotor reactance. Again, it is per phase. But one word also you add. At stand still. What is the meaning of stand still? At starting. It meaning is at starting when motor is not running. Still condition means starting. It means when N is 0 and slip is 1. Therefore, but when we write na XX2, that is rotor resistance per phase under running condition. When motor is running with slip S. Under running condition, slip is with slip S. Okay. Correct. Same like this E2 is stand still condition. It is a induced EMF, rotor EMF, rotor circuit EMF per phase again. At stand still condition or XX2 is under running condition. Okay, dear. Under running condition. Now you get understand na, because rotor parameter are changed at stand still and running condition. Okay. So this is your E2 means it is at stand still condition. Rotor EMF between two slip ring. Okay. This is the E2. इसको हटाते हैं 50 वोल्ट. Therefore, we can calculate E2 equals to per phase 50 by root 3. What is the value, please?
28.87.
See, 50 divided by root 3.
28.87.
Very good. 28.867 volt. Now, fast we write. Just take a minute. Here, another parameter are, it has a resistance. Means resistance
XL
is
4.5.
very good. 4.5 ohm. This is also, it is per phase.
Yes, sir.
We write here per phase. This is also per phase. Now, X2 also given. Sorry, here. Oh, this is here, it is wrong. Mistakenly the resistance. It is a reactance. Okay, dear. Because reactance is change. And a resistance of 2 times resistance is not there. And resistance is fixed. It not vary with sleep. Okay, dear. So actually this first part, it is a reactance. Okay.
XL.
Excellent. XL means we write it X2 means rotor reactance. And rotor, this is rotor resistance is given point. And always please remember, resistance is not greater than 1 ohm. Because winding has and reactance is more, okay, higher than resistance, okay, always. This is also per phase, okay, per phase. Now R2 X2 is over. Now what he say? Now he say that at stand still on open circuit. Open circuit means what? My dear, these things are not there. Now you measure the voltage here. Means open, like okay. Sorry, open circuit means when we give the rated voltage to stator. Okay. Generally, this is in normal running condition. It is a short with like this. Okay. Now he say that in stator, sorry, there is a stator also, no? Here maybe like it is delta connected or whatever. This is your stator. Now here we give the rated voltage. Okay, this is your stator. This is rotor. So, when we do the open circuit test, and the power factor at starting when slip rings are short circuited. Okay. So when we open this, then we measure this voltage. This is under open circuit. Now when they are short circuit, now he said that find the current and power factor. Okay, dear. It is very simple. Now you draw the equivalent circuit of rotor per phase. Hello? Just a minute. Here, this is the rotor resistance. This is reactance. And this is your circuit, okay? Here now, this is XE2. This is R2. This is XX2. Okay, now he's asking the current I2 and cos phi 2. So first of all, At starting. So at starting he is asking, huh? At starting. So you know at starting, just a minute. At starting n equals to 0. Okay. Sleep is 1. Then you know, just a minute. Your rotor current is per phase. E2, because this is 1 only, no? Then it is E2 by impedance. Impedance is R2 square plus XX means X2 only. Okay, this is 1 become, no? Slip is 1. So this is the rotor current and power factor. It comes this much ampere per phase. Okay. And your cos phi power factor, it is R2 by again Z2. Okay. R2 by, this is what is the Z? Z2 is your R2 square plus XX2 whole square. So your rotor impedance is okay, dear. Now you got, now these values are there. Just put and calculate. Huh? Got it?
Okay, sir.
Yes, sir.
Thank you very much. Huh? I share this formulas. You please enjoy at home, huh? As a homework.
Okay, sir.
Okay, dear. What is the message is going? Okay, dear. Huh? Good night.
Okay, sir. Good night.